So we know that with related rates, we're always going to be involving time. We're always going to start off with some sort of a starting equation, either algebraic or geometric, or in this case, even trig equation before the d over dt, the calculus portion comes in. So it says in the right triangle shown, the angle theta is increasing at a constant rate. So whenever we have a problem where theta is involved, it's always going to be in relation to a right triangle. So if you know theta is involved and the right triangles is involved, you know it's always going to be sine, cosine, or tangent. Okay, it's always going to be involving one of those trig equations. Okay, so we're going to have to pick a trig equation that's going to hit all the variables that's involved, or all the information that's involved in the triangle here. So we have theta. Okay, let me read the problem here. The right triangle shown, angle theta is increasing at a constant rate of 2 radians per hour. At what rate is the side length x increasing when x equals 4 feet? Okay, so we know we have to involve trig somehow. Either sine, cosine, or tangent. Now we have theta, x, and phi shown in the triangle, so that indicates to us that those are the most important parts that we have to involve. So which trig equation will allow us to hit those two sides in that angle? Sine, right? So sine theta equals x over 5. So that is going to be your starting equation. So just like with previous related rates problem, we always start off with some starting equation that we recognize, right? And then the calculus comes after we build that starting point. Okay, so sine theta equals x over 5. Let's go ahead and set this up so that we can find the derivative. I like to have a 1/5 out in front. This feels cleaner and easier. It doesn't feel like you have to involve anything complicated like quotient rule. It's just a easy power rule on the right side. Okay, so let's go ahead and find the derivative. Get the calculus out of the way, see all the different variables that's involved. Okay, so sine theta's derivative becomes cosine's derivative. Cosine. But we have to include what? Because of related rates. D theta dt. Okay. Okay, 1/5 x becomes 1/5 dx, right? So related rates, every variable is going to get impacted by time. Okay, so there we end the calculus portion. Now we're just trying to find a way to replace everything that we see. Okay, so let's go back to the problem. Let's read what we have. Angle theta is increasing at a constant rate of 2 radians per hour. Okay, so what variable can hold that information? D theta dt. Positive or negative? Positive because increase. Okay. At what rate is the side length x increasing? What are we looking for? Dx dt. When x is 4 feet. Okay, so let's see what we have here. We have d theta dt, which is 2, so that's a perfect replacement. We're looking for dx dt. That's good because we have that variable out. But what we need to find a replacement for is cosine of theta, okay, which we don't have explicitly yet, but we can find it. Okay. Understand that with trig related rates, you're not looking for theta. Okay, you're looking for cosine of theta, okay, which is a trig ratio, which is going to come from this triangle that we have here. So what I like to do is I like to redraw the triangle and label the parts as much as I can. Okay, so I know this is 5. I know at this moment x is what? 4. And then Pythagorean theorem tells us the missing side length is what? 3, right? 3, 4, 5 triangle. So from this information, we can gather that cosine of theta must be what? 3 over 5. So that's the hard part. That's the unique part about these trig related rates is you have to create another triangle to get the ratio replacement for your trig function. and then you're in the clear. Now you can just find the variable that you're looking for. Okay, so now I can make my replacement. Cosine theta is 3/5. D theta dt is +2. And I'm just solving for dx dt. Okay. 3 times 2 is 6. 6/5 equals 1/5 dx dt. Divide by 1/5, the same thing as multiplying by 5 on the other side. The 5's reduce. Dx dt is just 6. And what's my unit of measure for dx dt? Feet per hour, yeah. If for some reason you're looking for d theta dt, then it's always going to be radians per time unit. Okay, never degrees, radians per time unit. Right, so this is the special type of problem that we did at the end of last semester when we were hitting trig unit and we're kind of going back and looking at everything from a trig perspective. And this is we did revisit related rates in December. So it's a little bit different because of that trig ratio that we have to find a replacement for. Okay. Okay, let me do one more type of problem, and that is so hopefully this is a good review for cones, but I want to do cylinders. Okay, cylinder has a very similar looking equation, but it's a lot easier to work with. There is no similar triangles, and there's something that we can do with the radius that we couldn't do here. Okay, so let me skip to page 11, which is part of your homework page. And I want to look at number 2. Okay, so whenever you see a cone problem, you're always kind of preparing your mind that, okay, I got to do similar triangles. I got to do ratio. It's going to be a little bit longer of a process. But when you see a cylinder problem, you should tell yourself that this is an easier problem. Okay, it will be an easier problem. So let's talk about why that is. A cylindrical tank with a radius of 5 centimeters is being filled with water at a rate of 3 cubic centimeters per minute. How fast is the height of the water increasing? Here's my volume formula. So the hint is that cylinder formula looks like the cone formula, but a cylinder, as in this case, has a radius that is a constant value. So that's the big distinction here, right? That as the water level is rising, is the radius changing? Is my radius going to change over time? What do you guys think? Versus a cone when the water level is increasing. You see the distinction here? All right, so as the radius is increasing, that radius is, as the height is increasing in the water level, we can expect that radius to remain the same, but for a cone, as the water level is rising, we expect that radius to increase over time, right? So that's why we have to hold on to our R variable. We couldn't replace a number because it's constantly changing. But here, your radius, if your radius starts at 5 centimeters, it doesn't matter where the water level is, it's going to stay 5 centimeters the entire way through. So if your radius is a constant value, there's no need for similar triangles, and it makes the problem a lot faster, a lot easier. So V equals pi r squared h. Your radius is 5 centimeters. You can just go ahead and get rid of that variable, and then instantly you have a much easier equation to work with. Okay, I see some students, they try to force this ratio into the problem, but it just doesn't fit, right? There's no need for it. Okay, so once you got rid of R, then you're already in terms of H, and you're ready to find the derivative. All right, so what does V become? dV dt. 25 pi is the coefficient. It just doesn't go anywhere. It stays. And then H becomes dH dt. Okay. Let's gather some information here. A cylindrical tank with radius 5, which you already found, is being filled at a rate of 3 cubic centimeters per minute. What is that referring to? EVT, right? You see cubic centimeters, that's indication you're dealing with volume. Minute, that's time. So volume and time, it must be dV dt. Positive or negative? Positive because being filled, right? So we know that the water in the tank is increasing, that volume is growing. How fast is the height of the water increasing? Yeah, we're looking for dH dt. So everything that we need is in front of us. We're just one piece away, right? We just replace 3 in for dV dt, and we solve for dH dt. Okay. So now solving for dH dt is just one procedure away, but we gotta be careful with what's a common mistake that students want to make here, or not one, but it's easy to make. Is this correct? What's wrong with this? Pi needs to be in the denominator, right? It doesn't look like a big deal, right? Because pi is in my answer. You know, what's wrong with this? This is a numerator location. Okay, we need to be in the denominator. So that small little difference is key. Okay. Okay, units of measure, centimeters per minute. Okay, so part B of topic 3 is extreme value theorem. I mean, are these important theorems? So, and also some of these problems may require the calculator. I think number 2 will. So if you can go to page 10, let me highlight these important theorems. I think EVT we've seen quite a lot of. We've brought up mean value theorem, and I want to just connect that with Rolle's theorem a little bit. Okay, so extreme value theorem, we saw it on the previous quiz. If a function is continuous on the closed interval, so extreme value theorem, we don't need differentiability because we're not trying to guarantee a slope. We just want to find the max and min. So as soon as we have continuity, that's all we need. That's the only condition that we need. Right, then the function must have a maximum y value and minimum y value. So here are the steps. We confirm that function is continuous. We identify endpoints, we identify critical points, and we test our critical points and our endpoints into our original function, and we just identify and we keep our answer is our y value. And so this is one of the more traditional problems that we started off with at the beginning of the semester. Find the value of the absolute extreme of the function 2x cubed minus 3x squared minus 12x plus 1 on the closed interval from -2 to 3. I'm trying to find an absolute max or min on the closed interval, so this must be extreme value theorem. So the only condition that's required is function needs to be what? Continuous. Is the function continuous? Yes, polynomial, right? There's no denominator variable. There's no asymptotes. So we know our function is continuous on the closed interval. Okay, next up, we need to find candidates. Our candidates comes from endpoints, which we already have, and critical points. And how do we find critical points? Yeah, find the what? Derivative, right? Now, if there was a numerator, well, let's say you found the derivative and there was a numerator and denominator within your derivative, then you're only looking at the numerator, just the numerator of f prime equal to 0. Okay, the denominator would tell you vertical asymptotes, which is not going to be a critical point for us. Okay, so we're going to find f prime, set f prime equal to 0, because if the whole point here is when we find f prime and say set equal to 0, we're basically looking for the peaks and valleys, right? And if we find the peaks and valleys, then we're looking for these candidates that could be the max and mins of our curve. Okay, set equal to 0, I can factor a 6 and just try to go through my factoring steps. Okay, how many candidates do we have? 4, right? 2 critical points and 2 endpoints. In what situations will we not include one of our critical points as our test point? It needs to be where? These has to be located inside the interval, right? So if something that's outside the interval is not part of our problem, so we have to always make sure that our critical points are inside the interval before we test it. Okay, so now we're going to test each of our 4 critical points, or 2 critical points and 2 endpoints, and we're going to test these against what? Insert them back into the original. Yeah, because we're looking for the physical locations, right? If we plug it back into the derivative, that's not going to, we're already done with the derivative, right? We've already found what we need from the derivative. We're not going to put it back in. So they all go back into the original function. Okay, so to save some time here, if you just put all this into the calculator, you're going to arrive at these y values. And the important thing is the y values. Okay, don't focus on the x value. Okay, it's the y value that's important. So if it's asking for absolute max, and it's multiple choice question, and your answer choice has 8 for one choice and -1 for the other, -1 will be incorrect. Okay, it's the 8 that the problem is looking for. So when you see this word here, value, I know it seems very vague, but this is talking about y values. Okay. Okay. Good with extreme value theorem. Okay, let's look at mean value theorem. Mean value theorem says if a function is continuous and differentiable, so if I can show that my graph is going to be smooth curve, then there exists a number such that whatever I find between the slope of endpoints, that's what this f of b minus f of a is equal to. So whatever slope that I'm able to achieve between the endpoints, that it could be 2, it could be 3, it could be 5, but whatever that number is, I can guarantee that there must be that slope behavior somewhere along the curve. So if there's a slope of 2, I can guarantee that there must be a slope of 2 somewhere along the slope of this curve. Okay. So basically it's saying that whatever slope I find between the endpoints, there's going to be an instance on the curve where the exact steepness is also that value. Okay, so here are the steps. We identify the slope between the endpoints. So that means we need to find the x values and find the order pairs and find the slope. Then separately, we're going to find the derivative of the function. Then we set the derivative equal to the slope. And when we do that, our goal with mean value theorem usually is trying to find where's the location on the curve where this specific behavior, the slope behavior is existing. That's what we're usually trying to do with mean value theorem. We're trying to, we know it's going to happen, and we have to usually find the location on that curve. Okay, so when you solve for the variable, you're locating the x value where the slope of the tangent is matching the slope of the secant, which is the average rate of change. Okay, so number 2 here, let f be the function defined by y equals x plus natural log of x. So that's my curve. What is the value of c for which the instantaneous rate of change is the same as the average rate of change over the interval from 1 to 4? So basically, we're just going to step through mean value theorem and go through our steps. Okay. Now, x and natural log of x, these are both smooth curves. We know our function are both continuous and differentiable. We don't have to, it's not required to state it within multiple choice question, but let's just treat it like a free response question here. So we know our function is continuous on the closed interval and differentiable on the open interval. Okay, so we have the x values, right? We have a and b. So what information should we try to find first? Okay, so step number 1 says identify the slope between the endpoints. Before we can find the slope, we first have to find what? Not the derivative. We're doing this later. We're just focusing on this side of it. So what information do we need if I want to find the slope? I'm going back to algebra, right? What information do I need if I want to find the slope between 2 points? Okay, so I have x of 1 and x of 2. I need to find the y values, right? How do I find the y values? Plug back into the original function, right? So there's no calculus involved, right? We're just trying to get to the slope. We're just trying to figure out what the y values are so that we can find the slope, okay? So we insert 1 into the function here, 1 plus natural log of 1. Natural log of 1 is 0, so 1 plus 0 is 1. Okay, we're going to need our calculator here. 1 plus natural log of 4. Natural log of 4 is not going to be a nice whole number value for us. It's going to be a decimal value for us. Oh, sorry, yeah, 4 plus natural log of 4. Okay, so 5.386. So now that I have my order pair, what information can I find for my order pair now? Find the slope. Yep. So change in y over change in x, right? So we have to do a lot of this setup work before we can get to the calculus portion of mean value theorem, right? We have to get this set up first before we can worry about the derivative and everything that comes after. Okay, so change in y over change in x. We're basically trying to figure out what this number is first before we can match with the derivative, right? Okay, so 5.386 minus 1 is 4.386 divided by 3. That ends up being 1.462. Okay, so now that's our target. We know that somewhere along the curve, there must be a slope on the curve that's exactly 1.462 because the slope between these two points is 1.462. So now we have this part of our formula figured out. Now I can focus my attention on what? Finding the derivative. Okay. So f prime of x equals x becomes 1. Natural log of x becomes 1 over x. So I set this equal to 1.462. Because that's exactly what mean value theorem is doing, right? We're setting the derivative equal to the slope. The reason why is because this is our slope formula. This is the slope that we're after. We're trying to figure out where on the curve is the slope of where on the graph is the slope going to hit 1.462. And it's going to be somewhere along that curve. We're trying to solve for x. That says, what is the value of c? That c is your x value, where the instantaneous rate of change, where the exact steepness is the same as the average rate of change. Average rate of change is this average slope, which is 1.462. Okay, so I can subtract 1, cross multiply, solve for x. And then your c value is guaranteed to be between what? Between 1 and 4, right? It's got to live on that interval. If you don't find a value between 1 and 4, that means something didn't go quite right. We were guaranteed at least one value. Now, if this ends up being really messy and you're not able to solve algebraically, then what you can do is you can set everything over to one side, set equal to 0, and then you can graph whatever this equation is, put it in the calculator, and then see where it intersects with the x-axis. Typically, I see the mistake that I see with mean value theorem is that I see students, they find the derivative too soon, and they end up finding the ordered pair using the derivative, and then that's incorrect, right? Then you're doing f prime of 4 minus f prime of 1 over 4 minus 1, which is not the same thing. So I always encourage students to focus on the algebra first, right? Get to your slope first, and then find the derivative. If you find the derivative too soon, you may be tempted to plug in 1 and 4 into the derivative, which is not part of our practice. Okay, number 3, Rolle's theorem. Very similar to mean value theorem. It's just that it's the same formula. It's just that the slope between the endpoints we're trying to guarantee not just any slope, right? Here, mean value theorem can adjust to any slope. Could be slope of 1.462, could be slope of -3, could be slope of 4. But with Rolle's theorem, we're trying to guarantee a slope of what? 0, right? So it's just very specific. We're just asking, okay, can I guarantee a slope of 0 rather than just any slope I find between the endpoints? Okay, so it's very specific. Rolle's theorem, if a function is continuous on a closed interval and differentiable on the open, and my endpoints have the same y value, then there exists a number where the slope or my derivative is equal to 0. So basically, if I can force f of a and f of b to be the same number, then that's going to guarantee that I'm going to get a 0 in the numerator. If I get a 0 in the numerator, that's going to be a 0 overall. So that's basically what Rolle's theorem is saying. It's I'm going to force, if I can show that my y values at the endpoints are the same, then I know f of b minus f of a will always produce a 0, which is what I'm trying to prove. Okay, so let f function be given by f of x. Find all the numbers of c that satisfies the conclusion such that f prime of c equal to 0. Now, when you see Rolle's theorem, you're going to step through the same steps as mean value theorem. Okay, it's just that when everything is said and done, you should be staring at a slope of 0 here instead of like 1.462. Okay, that's the only difference. Okay, so same things here. We're still going to take our ordered pairs, plug into the function, and get the y values. Okay, same steps. We have a polynomial, so our function is continuous and differentiable, just like before. Okay, f of 0. F of 3. Slope between the endpoints. So I want you to look at Rolle's theorem and mean value theorem, and I don't want you to think of it as two separate things. I want you to think of it as it's basically the same exact theorem. It's just that when I get to my slope, my mean value theorem can be anything, but Rolle's theorem has to be 0. That's the only difference, right? But the procedure is all the same. You're still stepping through the same condition. You're still going through the same steps. You're still finding slope between the endpoints. You're still saying the derivative equal to your slope between the endpoints. The only difference is this can be any number. This has to be 0. That's the only difference. Okay, so now we're going to find what? Yeah, we're done with this portion of the process. Now we're going to focus on the derivative portion. We go through a power rule. And now we set our derivative equal to the slope that we found. Want to know where on this curve, now that I can guarantee a slope of 0, now I'm asking where on this curve, where on this graph is the slope going to be exactly 0? Looking for an X location. Okay. I have to involve the square root, but when I take the square root, what's going to happen? Plus or minus, right? But what's the only location that I want to involve? The positive, right? Because I have to live within my interval. The negative root 3 is outside my interval. So my C is just positive root 3. Okay, so I want to review extreme value theorem, but I also wanted us to make sure that we understood that mean value theorem and Rolle's theorem is just the same thing. It's just Rolle's theorem is just the pickier version of mean value theorem. You got to give it a specific result. Otherwise, it doesn't quite fulfill Rolle's theorem. Now, if these were not the same numbers, Rolle's theorem would not apply. But what would still apply? Mean value theorem would still apply, right? Because we can still guarantee a slope. It's just we can't guarantee a slope of 0 anymore. Okay, I like to just spend some time hitting some of the homework problems on page 11 and 12 that you guys are going to do. So on page Okay, why don't we do some more mean value theorem and Rolle's theorem? So let's look at number 3 on page 11. Okay, it says let f be a differentiable function. So if they say differentiable, that means it also assumes that it's continuous, right? So if it's differentiable, we know it must be continuous. So a lot of times the problem may not say continuous and differentiable, because if you go after the more the one that requires a more difficult circumstance, that means we know that it must be continuous as well. So if it's differentiable, it's got to be continuous. Okay, so we have order pairs, endpoints being 0, -4, and 10, 11. Which of the following must be true on the interval? So we have information about EVT, we got MVT. So we see MVT involved, so let's just go through and find the slope, right? Because whatever slope that we can discover here, we can guarantee that that slope must exist somewhere on that curve. So f of 10 minus f of 0, or 10 minus 0. So 11 minus -4. Ends up giving us 15 over 10. So we know that this, whatever the slope is, it's got to be guaranteed somewhere on the curve. So I know by mean value theorem, this must be true. Okay, so this is a guarantee here. So we know that the slope between the endpoints is 1.5. And somewhere along this curve, there must be a steepness on the curve that's exactly matching 1.5. Okay, so let's look at our answer choice here. F prime is equal to 0 since EVT applies. Does this make sense? No, okay. F prime C equals 11 plus -4 over 10 minus 0, since mean value theorem applies. It's a little bit off, right? That plus, it should be changing y over changing x, not a plus there. F prime of C equals 11 minus -4 over 10 minus 0. Okay, so this matches what we know to be true. F prime of C equals 1.5 since IVT applies. So yeah, this is the wrong theorem, right? Wrong theorem. Okay, read number 4 and see if you can make sense of that. I'll go over that with you. And the hint is you got to consider the denominator. Okay, what does the denominator of a function tell us about the graph? Vertical asymptotes. Okay, so can mean value theorem exist across vertical asymptote? Because the condition for mean value theorem is that the function must be what? Continuous and differentiable. Well, as long as for most of our problems, if it's continuous, it's always going to be differentiable. There's a few cases that it's not, but most of our problems is if you can make it past that first condition, chances are it'll pass that second condition. But there's vertical asymptotes where 4 and -2. So if you were trying to span an interval that is trying to go across the vertical asymptote, we know that can't happen. But mean value theorem can exist in all the other intervals because every place else is continuous. So which ones can we eliminate because there's a vertical asymptote that's impacting the interval? Okay, is negative 1 to 3, is this okay, or can we eliminate that? All right, negative 1 to 3 is not going to be continuous because of that negative 2 and I'm sorry by this number 2 can't. 1 only, right? Negative 1 to 3. Wait, this is okay, right? My bad. Negative 1 to 3 is okay because if my asymptote is at negative 2, 4, okay, sorry, negative 1 to 3 is okay, right? Because it doesn't not gonna try to cross the asymptote. 5 to 7 is okay because it's not going to cross the asymptote. Yeah, 1 to 5 is the issue, right? If I try to go 1 to 5, it's going to try to cross over that asymptote, and that doesn't fulfill. We can't guarantee that to apply for mean value theorem. Okay, so it says which can the mean value theorem apply? So 1 and 2 only. Yeah, question. So it's outside, right? So these are the only places where there's an issue. Everywhere else, we're okay because there's not going to be any other asymptotes that's going to impact the problem except those two. Okay, last one here, number 12. Sorry, page 12, number 5. Okay, selected values of a continuous function are given in the table. So remember, notice that it only says continuous here, so it doesn't specify differentiability, which means that we can't guarantee that's a smooth curve all the way through. So just be aware of that. We only know that it's continuous. By IVT, there exists a value such that f of c equals 10. So can I guarantee that by looking at the graph that my graph is going to somehow hit 10, a y value of 10 somewhere along this interval? Yes. Yes. Why is this true? Okay, continuous. Okay. Also, why? All right. So if I start at y value of 1, and if I end up at y value of 14, I have to do what? Right. It's got to cross 10 somewhere along the way, right? Because I know it's continuous, so it's got to hit every y value between my lowest and highest. Okay. So we know this is true, but we're looking for false. Okay. By mean value theorem, there exists a value such that f prime of c is equal to 10. Now, if we wanted to show that this is true with mean value theorem, we can pick between 2 and 5, find the slope, 31 minus 14 divided by 5 minus 3. But we can't even get that far because why? Mean value theorem requires which condition? Differentiability, right? It doesn't specify that. It only says continuous, so we can't guarantee that it's a smooth curve all the way through. There may be a sudden sharp turn that's impacting us to be able to make this conclusion. Okay, so no, that's false. That's the sorry, this is false, which is our correct answer. But I want to keep looking at the other ones here. By EVT, there exists a value such that f of c is less than or equal to f of x for all x on the interval from 2 to 5. So that means we can EVT only requires continuity. So so we know that we can hit all of our lowest and highest Y values guaranteed. So it's really coming down to that condition there. So IVT, extreme value theorem, they only require continuity. The only theorems that require differentiability are the ones that has a slope component. So only mean value theorem and Rolle's has a slope component that we're trying to guarantee. Okay, so tomorrow I'm going to check pages 9 through 12. And then we're going to try to finish up the topics in packet 2. All right, go get your phones. Okay.
But I would just find. How did you know this? The answer is to.
Oh, okay. The reason why is because you have to grab it. And then look what you have to have that. You have to grab it and look and see that actually cross the other side.
Okay, okay.
That like what is changed. Sure. That's actually here.
Can I do tomorrow morning to take a break?
Okay, so- Thank you.
I should have looked at my paper history. Actually, I was part of I think once they're big. And because I've done a test. Oh, I know it's more people. This is not the test. Making sure I didn't say it. No, I probably. It's just something short.
The 18 professional, so I didn't know which you could use.
Okay.
And I think the basic.
So, it's affecting, one through 4, 5 through 8. So yes, it is. That'll be good.
You had that.
Yeah, this is, yeah, you just other questions, so you can just do like cosine squared, get that decimal value. Because you can't, it's hard to put the in the calculator, but we can do it. We can do 1 over cosine.
Okay.
Let's see if that works. Times events. I can finish the whole. Okay, all right. Number 2 is true because there's only 2 asymptotes, right? The only asymptote is that -2. So it's. So everywhere else, it's going to be fine. The only places that there's an issue is at -2. So anything 5 to 7 is safe because there's only 2 places.
Thank you.
Okay, thank you.
Thank you.
Bye. Because interval from 1 to 5 is trying to cut across.
I could, I used to like. Text at 8 and 5.